kind of talk about some of the stuff that I have going on with my team, as well as some things that I've been seeing, just so we can potentially help everybody learn how to do some basic engineerings of drivetrains, bases, and just really understanding what it takes to make a decent robot that is reliable. So this is actually Team 2048B. This is their drivetrain. You can see a primary support beam right here. Now this is actually an example of something that's not ideal, but it's a basic understanding of the drivetrain. So one thing I want to note is I've seen a lot of different situations where you'll have simply the motor over here going to a gear and a support structure like you see here, and then just the wheels and stuff, and everything's kind of just bouncing around, and typically not a very good setup. Now, something that I always instill into my teams is to have an actual framed structure of some sort. So I'm just going to draw on here so you really understand. And this is what they're working towards. Now, this is the base drive system off of the Herobot. So you can see something that I really hate here. This is actually pins. So as opposed to having an axle, we just have basic pins holding these in, and I really dislike that as far as a design because what that allows these gears to do is flex and move around way too much. The ideal situation, as you see here, is having an axle, and I'll show you some photos of the future drivetrain from RoboBros and what they did, but this is a really good video just to kind of see what we have here. So again, we have the main motor mounted in. That goes to this drive axle we see right here. So that goes straight to the motor. And then this is the base of the structure that's going to be housing both the gears and the wheels. So what we have here is the front and the back, and then there will be a primary structure that goes across here. And then ideally, RoboBros replaces those pins with axles. So I'm going to then bring in this next photo. We kind of review how it ends up looking once we get better structure built. And unfortunately, it's a little bit blurry, but I think you understand what's happening here. Let me actually pull this picture into the editor so you guys can see how this looks. No, I don't want to save all that. Alright, I'm going to zoom in on this so you guys can kind of take a look and see what we have right here. So again, this is RoboBros. This is as they're rebuilding from the drivetrain. You see this is, let's change that color. This is that support structure we were looking at before. Unfortunately, this photo turns out to be a little bit grainy, but you have the inside and outside beams right there. And then what you see is that front beam going across, and there's going to be another one in the rear. Now note, a lot of those pins that we saw were replaced by axles, so this helps strengthen the overall drivetrain, makes everything better. And then something really important to look at, since not only we have the base of a drivetrain, but everything that you add to your robot, I really try to enforce that there's equal weight distribution to both sides of the axles of your drive system. So I'm going to get rid of those lines. Now notice right here, that's where we have weight coming down. We have weight coming down, and this is actually going to be the structure that houses all the gearing and everything for their 4-bar. So you see all those yellow lines coming down to the drivetrain. Now the important aspect is, as we have weight going down in this direction, let me just go ahead and make a quick little arrow to help make this easier to see. So we have weight moving down, right? I want to always see equal distribution of the weight that comes down on the two sections of that drivetrain, so both the inside and the outside. What that does is it helps alleviate the flex that you see a lot of times with a lot of robots that are just not designed very well. The center point right here will flex inward. Now notice, part of what we do to help keep that from happening is all the pins that we have connected here to the back end of this drivetrain, and then we have a solid 2x that goes from the left side to the right side. And you'll see we have this 2x, and there's another one going straight across here. That's what creates a nice either rectangular or square shape, so you have a solid drivetrain to build everything off of. So I'm going to get rid of a lot of that stuff again. Now just notice these big 4x, so that's where all the weight comes from. And I'm going to pull in another picture here from RoboBros. So this is the RoboBros robot with a lot more built into it. You can see here that they extended this upright. We'll switch that color. All right, so they extended this upright here. So we have a little bit more height than when they did that, specifically so these rubber bands that are creating some tension to help lift their head get a little bit more tension with this additional height. We still have that solid 4-bar. Now you again notice we have this really nice rectangle, and again this is just the basics of engineering a good drivetrain with VEX IQ. You have that nice rectangular drivetrain. Sometimes you can have, say, another one in here where inside this smaller section you have just the gears, and then inside this outer section you have just the wheels. You can say one can be better, but in reality, this overall design just helps these drive bases be reliable, and this is beneficial not only for driving, but for the aspect of programming. Once you start programming things, you really want to start focusing on having a really good drivetrain and just basic understanding of engineering so you can help ensure the robot performs properly, especially when you're doing the engineering aspect. Now, again, notice a lot of those aspects for just keeping things square and straight gets transferred over to what they ended up designing for their intake head. You can see that nice perfect rectangle, and then here they actually did that insert for the gearbox, so they have a perfect set gearbox right there where all the gears are, and then on the outside here we have the wheels. So everything was based off those gears, and the wheels can move forward and backward, up and down based on how they tweak things to really get that intake to work. And then a lot of the same stuff transferred over here as far as getting that set up, the engineering of having the two sides connected so you really get some good strength right there. A lot of the stuff really came well for them once they started designing all of this nice structure and getting everything organized in a very strong fashion. I'm going to pull in another one. So here again, we zoom in a little bit on the RoboBros photo again. It is a little bit blurry, sorry about that, but that's, well, I think you see really everything we need to see. So now take a look again. We have these uprights, right? This is what we saw before. Now they added a lot of their gearing. You can see a really important aspect is they do have one solid axle from the left motor and right motor, and this is for their 4-bar. That goes to this primary gear axle. Get rid of that so you can see a little bit better. So we have small gears in the bottom, and you see a bunch of gears and things in here, and this is really just all for space. They wanted to make sure that these gears that are right there connecting to the large gear do not move left and right. So we make sure we have a really good gear mesh. So you see then we have the 1-bys for the lifting mechanism, gets sandwiched right in the middle of all that. And then we have extra axles going between these, and these really just help to keep the larger gears that are driving all of the force to lift the head and make sure to keep that from twisting and getting really kind of kittywampus. And then we do have this solid gear that goes all the way through all of them. And notice something important here, okay? So this axle that goes through all of them not only goes through all the gears, but goes through all the uprights. So all of the power that's transferred to the head is on this axle right here. Everything that makes the entire head move is based off of that axle. So we want that to stay straight. We want really good gear mesh going to the drive axle, and that's something they really accomplished. They spent a lot of time on re-engineering that continuously to make sure we had something working really well. So moving on, I want to talk a little bit more about the Nerds robot. So this is 2048N. So here's the N drivetrain, and again, this is really just talking about the value of a well-engineered drivetrain. Here's the front plate. And then you can see a lot of similarities with 2048B, the Robo Bros. We have this perfect rectangle here, and then we have an axle going through, an axle for that motor, an axle for the wheel itself, an axle coming through. Now, again, the important part is having the structure on both sides of the wheels. You don't want that to flex, and again, you really help to alleviate the possibility of flexing when you have these big solid bars running across the front, and there's another one here or across the back, but you can't quite see that in that photo. And the same thing with the Robo Bros, right? They have this big upright that goes through, this big upright that goes all the way up to the top, so all the weight for all of that system is brought back down to these points, equally distributing that weight out to the outsides of that drive base. So that's a really important aspect. Obviously, everything is built off your drive base. If your drive base has issues, your entire robot's going to have some issues. So it's really important when you start at the base level to get a really good drive base. Now I'm going to bring in lockdown. We're going to talk about this a little bit more. So let's look at the lockdown drive base. All right, so here's lockdown drive base. Now, again, this photo is a little bit blurry just the way that I copied it over, but I wanted to make sure to get this video in. Notice something that they did a little bit different with their engineering. These guys have been doing this a long time, and I've taught them a lot, but with the way they brought the head down in order to have the section where they can lift up that one by, they needed to be able to tuck that in. So as opposed to the solid beam that we typically have across the outside, they re-engineered that in a really slick way to bring that weight over, move it, and then they have the cross beam right here. Notice all the support structure to interconnect all that. And then it comes back up and then moves back out. So you see that is lacking that big solid support that we normally do with our drive bases, but they accomplish the same concept by making this big kind of U pattern and reinforcing the heck out of it to make sure it stayed square. Now, again, the same concept here, right? We have these solid beams that are running on both sides. Here we have the drive axle for the wheel itself. Then we have the axle for a gear, axle for the gear, axle for a gear. Notice something I'm just going to point out on the other side. This is a really important aspect too that I see a lot of teams not implementing. You need to have a really good way to ensure that these wheels and these gears do not move pretty much at all, so you don't want to lose your gear mesh. That's a really important aspect to ensuring that you have a really good drive basis to make sure you have a good gear mesh that doesn't lose. Notice we have all these stoppers right here, okay? And then on the outside, we do have either a washer or a spacer. And then tucked right in here, you can't see it, there is a washer. That's another really important aspect to designing a really good drive base, is you want to make sure that you have a situation where anything that is going to be in motion does not directly come in contact with something that's going to be stationary. So this side of the structure is obviously stationary. These gears are continuously spinning. We do not want a situation where this gear is actually going to be rubbing on this structure. That's where we will always make sure to stick a washer or a spacer in there in that very small space to make sure that we don't have any rubbing from the outside of this gear to the structure or the inside of that gear to the structure. We don't want a situation where we're rubbing. That you lose a lot of your speed, you lose a lot of your torque, you have a lot of issues with your drive base if you start forgetting to put washers and spacers in there between anything that's in motion and anything that's stationary. Obviously, we can see a lot of the same situations with the Robo Bros and the Nerds, where we have a lot of main support structure. So that's going to be the main piece that comes down, and then we have some more support structure that come down and interface directly with this drive base. Same thing coming down. Notice all of the structure that helps to ensure that the weight is properly distributed. This is one square piece, another square piece, another square piece, another square piece. You see all of these connections. This makes sure that this drive base and then everything that connects to it is solid and strong. That's really important aspects to designing a good robot. I'm going to bring in another top-down view from Lockdown. All right, here's the Lockdown 2048A robot. Obviously, we're a little blurry on this one too. You can see a lot of the videos and how it is set up. So this is one of the more recent designs of the claw system. You can see right here. We'll be doing some more videos showing off how that has been working with 2048A. Has been working a lot on making it as optimized and perfect as possible. But going back to the drive base, right? This is that solid structure. And here we have the solid structure coming off of it. On the inside, there's more solid structure. On the very big core of it, right in the dead of center, more solid structure. And then this is the arm. And then notice the dual large gears right here. Everything ties in and it's solidified, and the core of this whole system, and honestly the core of every good robot, is a really, really good drive base. Remember, we have that little U shape that's going to be underneath there, and then here we have a good solid front section. But notice every robot that one of the 2048 teams is always running has a solid drive base to it, and it's a really important aspect to ensure you're doing that. You want to keep square, you want to keep things solid and strong, and that's just going to make things so much better. Now I want to talk about another robot that another coach sent me some photos of. So let's take a look at what we're looking at here. All right, so I don't want to specifically talk about who this team is. I don't think we have a team number or anything here, but I want to talk about a lot of the same concepts that I talked about with all my other teams that are missing in this situation. So we do right here have some primary structure, but notice what we don't have. We don't have the outside section of that gear and wheel base, so we don't have the ability to really have good weight distribution. Going into weight distribution, we have this primary beam structure that goes from the inside of this beam upward. So what that's going to do is the center of the robot from left to right is here. Everything's going to want to flex in automatically just because all of your weight for everything that you're designing is really built off of this one connection point that comes down to this connection beam. Okay, so that's a lot of issues right there. The same thing with this axle that comes through, both this one and then that top one right there. There's no outside structure, so you have the capability of this system coming through, but there's nothing on the outside to tie in the other side of that axle. So what ends up happening is this axle can move up and down, especially when you get a lot of torque that's going through here. Let me change colors. So when these two gears mesh, right, what's going to be happening is you're going to have a lot of force going down, and you're also going to have a lot of force upward from these gears meshing together. So what's going to want to happen is these gears want to push apart from each other as this system lifts upward, right? So as that torque is applied, you're going to have issues where these gears will start to lose their mesh. Now, it might not be a situation in this particular situation because there's not a lot of weight in that head, but you always want to have a situation where the axle has both an inside and an outside beam to ensure it's got really, really strong connection point. Now, we have what looks like the beginning of a 4-bar here. An important aspect to remember with the 4-bar, if we're looking at where this axle is and then this connection point, okay? I'll usually say using a 1-by is your best case scenario, so you get a lot more lift. You do lose a little bit rigidity, but there's a lot of ways to get around that. You can see with Lockdown and Nerds and Robo Bros, they all have a 4-bar of some fashion, but a lot of times we'll implement the 1-bys. An important aspect to remember, let's go ahead and do the circles. So the center pin of this point and the center pin of this point, these should be 100% lined up perpendicular to your drive base. Okay, it should be straight up and down. Now, this measurement from this point to this point should always be exactly the same as this point to this point. That's the core of how a proper forward bar will operate, because then you have this arm and this arm, and then as you raise this head by enacting those gears, these two bars should always remain parallel. And what we see here is this bar and this bar is absolutely not parallel. That's definitely an issue, and that's going to create that's going to make this head tilt funny as it lifts. Something else I want to talk about is, if we look at the head here, we look at how it connects. That's just a pin, okay? That's really asking for problems, because once you start applying force on there, you're going to have a lot of twisting that's going to occur. Ideally, I'd like to see an axle either go all the way through, or we would have just a simple axle right here that then connects to another connection point on this side, and then the one bar goes right through the middle, so it gives it a pivot point. Same situation down here. Now, again, talking about the drive base, right? We have this solid beam right here. Here's our motor, and then again, we don't have an outside piece, which I really would like to see. But here's our motor that goes right through, and then here's a transfer gear, and then we have the wheel itself. Notice that rear one is an omni wheel, okay? So when this motor system engages, this wheel is going to want to turn. I do believe the exact same thing is set up on the other side. Something that I noticed right off the bat, if we look at this drive system right here, what I see is a solid axle, okay? On the inside of these wheels, we do have square holes, and that's made to engage with that axle. Now, the issue is when you have force from your drivetrain going forward from this wheel and this drive system over here, what you're going to have is force going forward, right? So that means this wheel is going to want to spin forward. Even though it's not engaged by gearing, it's going to want to spin forward. Okay? That works out well when you're just trying to drive forward. Okay? If your whole robot's trying to go in that forward direction, I don't know which way is forward and backward of this one, but I'm just going to assume since the brain's over there, that this way is forward. If it tries to go forward, that works out well. The problem really comes in when this side wants to go forward. Now think about what happens if you're going to turn. Okay? That side goes to forward, this side goes reverse. The issue there is this axle is going to be caught in the middle, because what's going to happen is the wheel on the forward side is going to be wanting to spin forward. That guy wants to go forward. The wheel on the reverse side to get you turn, this wheel is going to want to go backwards. Now that's not possible since we have a solid axle. Okay, so what I suspect is happening if you guys are trying to turn is these wheels are really just dragging. They're not engaging forward and backward in any fashion. They're actually creating resistance for your turn, so every turn is going to be less accurate. And I do imagine that if you try to do any programming or auton on this type of thing, you're going to have a lot of problem, because these wheels are not allowed to spin freely, or they're not allowed to work in tandem with this one. Now, we do know that there is a diameter difference between a standard rubber wheel and an omni wheel. So that means your robot itself is not going to be perfectly level on whatever your playing surface might be. There's a whole lot of issues here as far as how this drive base is set up and what you want it to do as far as trying to be accurate. I would suggest really looking into separating these two wheels in terms of not having a solid axle there. And what would be the ideal situation would simply to be having a omni wheel on the outside right here. You got your omni wheel here, but we also need to really get good frame structure on the inside and outside. That way you can have an axle that goes all the way through and an axle that goes all the way through. And then you're probably going to end up having a transfer in here somewhere, and then another axle going all the way through for that wheel. Okay? There's a lot of stuff that definitely can be kind of rectified to make sure we have a good, solid drive base that this is just lacking in many ways. The nice part is you do have a decent amount of structure, it looks like, across that rear that helps support this. So you might not have a whole lot of sag in the center, but this would be overall improved vastly by having a good rectangular, properly engineered drive base that you then bring down the weight on both sides of that drive base. And then again, we still have that 4-bar situation where these are always supposed to be equal and parallel. So I would suggest we look at doing a 1-by here and another 1-by here with axles that properly support that so we can pivot properly. And I'm not 100% positive, but this rubber band actually looks like it's a legal size. I do believe there is size 32 and size 64 are the legal sizes for VEX IQ. You can use the actual VEX IQ official rubber bands. You can purchase other rubber bands as long as they are of the appropriate size. And again, I do believe it's 32 and 64. I'm not 100% positive on that, but you need to really double check and make sure that you're using all legal parts, because again, that is an issue. Now we're looking at that setup there. Let's just talk about this. Okay, this connection on the top, there's a lot of problems with that. Since you have so much force coming down on this rubber band, once you do have a legal rubber band on there, what you're going to have is a situation where this is going to be wanting to bend down this way. And then you're going to also want to have a situation where this system is going to want to twist because you have so much force pulling it forward as well, since this point is connected up here. Okay, the more ideal situation would be to have a good solid support structure going across the top that has beams in this fashion as well as what you have back here, but have that across the front, and then it ties into the outside. What I'm going to do here, let's see if I can find a picture of, I don't really see one. I need to get a good picture of, here we go, Robo Bros. I'm going to pull this one over. All right, going back here to Robo Bros. This is a quick little picture just talking about this. Look at that support structure here. I'm going to change that color so it's easier to see. Then we have this one here. Then we have the back one there. And I do believe they have a bottom one on there as well. So that creates a full square. And then we have a connection points in the middle. And then it's connected to that outside piece. And then we notice we have this support structure coming up off of that 4-bar, and this support structure off of that 4-bar. So all of the weight, all of the torque, everything from the rubber bands going down the head, etc., it all gets properly distributed down to our drive base. Okay, that all comes back down to having good weight distribution. Everything comes down the drive base. So we don't have twisting. We don't have a lot of movement. It's really well balanced. These guys did slap a handful of weights on the rear just to help offset the weight of this, especially when it's lifting. But this is a really good design overall. And again, I want to talk about, you see this 1-by right here, and that's their other 1-by. And then these points are always the exact same distance from one another, and then these 1-bys are always going to be parallel to one another. This 1-by, as it moves, is going to be exactly parallel to this 1-by. Now let's bring in that other robot again. So talking about this robot again, now we see a lot of the same issues that we kind of just talked about. There is a pretty good base structure here as far as the layout of what's supposed to be the claw system. So we do have some decent layouts here. We got that nice 90-degree turn right there. Okay, these don't articulate on the outside. It looks like the inside does the articulation to help grab those pins. So I do believe the whole point here is be able to grab pins in these 2 different points, grab them, and then flip them backwards. Now, if we can't lift that 1-by onto another pin, then that means these pins that they connect will not be fully nested anyway, so there might be some other stuff to address. But again, looking at a lot of that stuff, if we look at, again, just that solid axle that goes across, that's not going to allow you to turn. We have issues with all the forces that are applied up here. Again, we have an illegal rubber band right here. There's a handful of things that really need to be looked at. I'm not positive about all the rubber band situations of why that's over here, but that's definitely something to analyze. But again, the structure of just this upright and not having a really good system here that we can design everything off of is, I think, hurting you overall as far as your weight distribution. Granted, the robot overall is very, very light, so you might have a lot of flex, but there are some issues there that definitely should be addressed. The one thing I do notice is we have a drive here that goes to this arm and the drive here that goes to this arm. What we don't, however, have is anything solid that goes from this side to this side. So that basically makes this entire side an entirely separate system. Okay, and this side entirely separate system. So what can happen is you can start lifting in an unequal fashion. That's not an arrow. So when you engage that motor group, right, you want it to lift equally on both sides, and you want all the power from these motors to be applied out to your head. What you're not getting is that combined power by having a transfer axle going across. So I want to talk about, let's bring in the gearing here. Let's see if I had that video. So here's a picture again of Robo Bros. All right, now if we're looking at Robo Bros, again, and we're giving away all the secrets here, but this is what I want. I want everybody to get better. We're not going to get better if we don't see better competition. Everybody needs to be able to learn these basics engineering aspects, and it's just something I want to help everybody with. So look at the motor here, both the left side and the right side, right? They're mounted facing inward. They're sandwiched perfectly between these two uprights, okay? And then we have a whole lot of pins that are interconnecting the motors to the inside 4x. Then you have one solid, perfectly cut axle that is recessed into both of these motors. So when these motors are engaged, or they get engaged, they are applying all of their force on that primary drive axle. Okay? So they are working together in every possible way. And then what happens is then we have that gear mesh that we see right along these points between those two different axles. Let's see if we can make a circle just to make that easier to understand what I'm saying. Right? We have gears in the bottom, gears in the top. We want that mesh primo. Again, another aspect is we have these gears impacting close to a lot of structure, right? So that gear mesh cannot push away from one another because we have all that structure helping to hold it together. Honestly, my preference would probably be to have another piece of frame structure coming down to help ensure that we can't get any flex on these axles, because it's very possible that this axle could flex outward just based on the torque that is applied when this mesh occurs, right? Because all the lifting weight of that head comes back to this gear mesh. So those are all important aspects. Let me see if I can bring up another one from this other robot. Alrighty, so here's the robot again. So this looks like the other side of the drive system. Everything is pretty much the same as the first side we looked at. But again, look, we have this solid piece right here, changing colors so you can see that better. And then we still have that solid axle going across. And these wheels don't have any drive power to them, which obviously if we have drive power to them right now, it would be a big issue because of that solid axle. One thing that is nice is this brain is really easy to access, and then we definitely do have some really good structure going straight across the back end, and that helps keep it from flexing in the rear where all the weight is from that brain and the battery. And then we have this structure right here that then interconnects with this, and then we have what looks like that 4x right here that everything is connected to. Now the biggest issue that I also see as far as this brain placement is you only have access to these ports. Okay, that might not be that big of a deal at this point in time just because you don't have a whole lot of things that are engaging and moving around, but only having access to one side of the ports is going to be quite problematic once you start adding more sensors and LEDs and buttons and all that kind of stuff for doing a lot of the different more complex aspects. So let's take a look. Let's see where we're at right here. Again, we're looking at the gear mesh right there, so we don't have outside support structure, so those are going to want to disconnect. I don't know if you have washers or spacers or anything here behind these gears, but that would be something important to think about. Again, when we start talking about that, anything that's in motion, coming in contact with anything that's stationary, we want to have something there between the two so we don't have any grinding or rubbing, losing a lot of power. So I think that's really everything that I have as far as covering some of this stuff and the basics of just these concepts of engineering in general. Hopefully this helped a lot of teams. Hopefully it helped this particular team. There's a lot of stuff here to learn, but again, when we're going back to understanding the basics of really just building systems in general, again, coming back here, looking at Lockdown 2048A. There's a lot of really basic engineering concepts that have been implemented very well. And that's something I'm really hoping to see with a lot of other robots in the future as more and more people learn how to design things properly and how to do proper weight distribution to really understand the value of a good drive base that everything comes off of, really understand the value of proper weight distribution, making sure everything stays square, making sure we don't have sag on the robot. There's a lot of stuff that I can see that are very easy improvements for a lot of teams, and just hopefully we'll see a lot of improvement as everybody just gets better and better and better. Well, hopefully you learned something today. Thank you guys for watching. If there's anything specifically that you might have questions on, if you want me to analyze your robot, if you want to send in some photos, I'd be happy to. We've been working with a lot of teams from all over the world over the past number of years since I've been doing VEX IQ, which I'm thinking we're going on in 12 years now. It's important to learn a lot of these basic concepts. Once you learn a lot of these basic concepts and implement them appropriately, all of your robots in the future, your competitions, everything will start getting a lot better for you once you have some really good basic understandings of engineering, of these drive systems, of weight distribution, etc. My name is Chris with Elevations. As always, I thank you for watching. Please like and subscribe today.